Classical mechanics. This explains how everyday objects move and interact. It is based on Newton's 3 laws of motion and can explain everything from flying footballs to planets orbiting the sun. It works well for everyday objects, but it stops working for very massive objects or small scales and very fast speeds. Electromagnetism. This describes the interaction between electric charges, electric fields, and magnetic fields. It says the electromagnetic force is one of 4 fundamental forces of nature, and is the dominant force between interactions of atoms and molecules. It has many applications to everyday items, such as batteries, light bulbs, and radios. Optics and acoustics. The optics branch looks at the properties and behaviors of light, such as reflecting, refracting, and diffracting. While acoustics looks at the waves inside of mediums, like sound waves, which also have standard wave properties like reflection and interference. Optics and acoustics have lots of uses in several different fields of study, and they both have many applications in everyday life. Thermodynamics. This branch of physics explores the relation between energy, entropy, heat, work, and temperature. It's based on the infamous laws of thermodynamics, and it has lots of applications in machinery such as washing machines, engines, and refrigerators. Statistical Mechanics. This branch explains how the behavior of large groups of particles lead to the properties we observe, such as temperature and pressure. It explains the macrostates' properties from the underlying microstates of the particles. It actually has a broad application in many fields due to its statistical nature. Quantum mechanics. This is the set of rules that determine how really small objects work and interact. It's probabilistic in nature, meaning that we don't have precise measurements, and it says that most things are discrete, meaning there are only specific quantities that they can be, like energy levels. A key idea is wave-particle duality, whereby objects at this scale also behave like a wave. It has uses in more specialized areas like lasers or quantum computing, or several other areas of physics. Nuclear physics. This branch looks at how the atomic nucleus works and interacts, such as radioactive decay, whereby an unstable nucleus loses energy by radiation. It also explains nuclear fission, where the nucleus of an atom splits into 2 or more smaller nuclei by releasing lots of energy in the process. And it explains fusion, where 2 or more atomic nuclei combine, releasing tremendous amounts of energy. Although limited in its applications, they are almost always very important. Atomic physics. This looks at the structure of atoms and how it interacts with particles, electric fields, and magnetic fields. It says that atoms have a central nucleus with electrons orbiting it in discrete energy levels, and it can absorb specific amounts of energy to cause the electron to move. You might think that nuclear and atomic physics sound similar, and you are correct. The main difference is that nuclear physics focuses on the nucleus of the atom, whereas atomic physics looks at the rest of the atom. Particle physics. This branch looks at the smallest things we know of, focusing on the fundamental particles and fundamental forces. The 4 fundamental forces of nature are electromagnetism, strong and weak nuclear interactions, and gravity. While the fundamental particles can either be classified as fermions, which make up ordinary matter we know and love, or bosons, which are responsible for carrying these fundamental forces. For instance, the photon is a boson that carries the electromagnetic force. Condensed matter physics. This branch looks at how solids and liquids get their unique properties from the underlying particles, such as their structure, conductivity, magnetism, or quantum effects. The applications are usually very specialized in creating materials that can do extremely specific things. Relativity. Founded by Einstein, it has 2 main theories, both of which heavily use reference frames. Special relativity looks at objects that are moving near the speed of light, It says that at these speeds, time will pass slower and length will contract in the direction of motion. General relativity looks at very massive and dense objects like black holes. It also says that time will pass slower near these objects and that space-time itself will bend due to the effects of gravity. Its applications are quite specific but crucial for some technology to work accurately. Cosmology is the study of the origin, evolution, and fate of the universe. Currently, we believe the universe started in a giant explosion called the Big Bang, and has been expanding ever since. This can happen again if gravity is stronger than the expansion of the universe. However, it's more likely that gravity will lose this battle, and instead everything will continuously get further away and disintegrate into radiation over time until there's nothing left of anything.